lecture. I'll wait until you settle in. So today is going to be about the law of large numbers in a game theoretic way. So I'll tell you what it is, sort of the classic measure theory rendering, and then we'll go through a game theoretic proof of a similar but stronger statement. And so we'll do it twice. So the first hour is about the bounded case, which is much simpler, and we'll really sort of go into the strategy that you need to get infinitely rich if the law fails. And sort of while we're developing this strategy, we'll see two important tools. So I think the authors use this sort of simple chapter to more or less introduce these. So they're called reinforcing and countering intersection. So that will be the workhorse themes that we use. And then after that, sort of making the strategy is going to be much, much easier. And then in the second half, so the second hour, we'll do the unbounded case. So that's harder, and we'll need two more tools. So we'll talk about upcrossings and about super and semi-martingales. Okay, so what is the law of the large numbers? I wanted to make an animation, but in the end I decided to just make a drawing. So the drawing is this. If you plot the average of a bunch of random variables, so let's make it very easy. So xi are going to be IID from P. So this is now really a probability measure, nothing game theoretic here. And let's say that they all have mean 0. And so you make a graph of this average as it develops. If you take more and more samples, then you see a picture that is random, so it's not always the same, but there is a sort of feel to what it looks like. And it looks like this. So this is the mean 0. So if you take a large enough expectation, a large enough average, then you'll just recover the mean. Right? And then you want to prove this, so the statement can become that, so this is the infinite version of this, is that if you take the limit as n goes to infinity of average, then it really is 0 with probability 1. Right, so I'm not assuming that you've ever seen this before, so I've been getting on quite well in life without. But this is you know this sort of intuition that if you average enough things that are all the same and random, then the randomness sort of disappears. But this is one way to make that formal. Okay. So we're going to do a game theoretic version of this. So the first thing that we need to do is we have to decide on what actually is the game we're going to play. What's the protocol, what's the moves. So it's going to be very similar to last week, a simple investment game where we can only do one thing. So the game will be as follows. We start out with 1 unit of, let's say, cash or evidence, how you want to call it. Let's think money. I like that analogy. Then we're going to do an infinite number of rounds. Okay. Each round, we, the skeptic, we're going to choose how many, we're going to gamble on the next outcome. So we're going to do that in the form of buying what's called these tickets. We saw that last week. And we're going to buy n of them. And we can get any number, positive or negative. The intuition is that if we think that the means of the data are actually higher than they should be, so it's not really looking like it's heading for average 0, then we typically want to buy a positive amount. And if we think it's going to be much too small, then we buy a negative amount. And if we think it's going to be okay, then we don't have to get very rich, right? And maybe we want to buy 0. That's also okay. All right, so after we announce this position that we take, the reality, so that's the other player, will produce for us the outcome, xn. And you can do this in whatever way you want. There's no assumption on how it has to relate to the other outcomes, for example. But we are going to assume that it's bounded. And just for simplicity, let's do -1, 1. Yeah, at the far end, I'll talk a little bit about variations of this, but just sort of a canonical bounded thing. And then our capital is going to grow from what it was by the number of tickets that we got that each pay xn. So this is why, if you think it's going to be high, you want to buy a positive amount, because then capital grows. If you think it's going to be small, you want to buy a negative amount. If you think it's going to be 0, then it doesn't matter. Good? So we're going to say that the skeptic wins if the capital is positive for all n. So you cannot go bankrupt. And so now we make a statement that will be the game theoretic version of what's inside there. So two things can happen. Either what's in here exactly happens. So it is true that the limit of the average, okay, I'm going to write this at least too many times this later, happens to be 0. So we're happy with that, because that's in a way what we think that random outcomes should have, this property. So if that happens, then we don't have any other obligations. But if it doesn't, then we have to be able to drive our capital to infinity. So we're going to get infinitely rich if the sequence fails to have a mean 0. So are you all familiar with the ways in which you can fail to have a limit? I'm sort of wondering, because the book doesn't spend any time on this. But if I ask you what can happen if the limit is not 0, do you know what cases you can have? So I'm assuming the answer is not really?
Not really.
So let me just draw a few pictures. So what are the cases in which you cannot have limit 0? So one of them is sort of easy to imagine. The limit is something else, right? That's wrong. But there are other cases, namely there is no limit, which can happen if the oscillations don't disappear. Right? So in that case, you can talk about the lim sub and the lim in, which are the limit of the peaks and the limit of the valleys, and they may not be equal. Right? So if they are equal, then the picture will look like this. Then there is a nice limit. If they are not equal, then there is oscillations forever. And that's also a case when the limit is just not defined. So those are the two things. Either the limit is just wrong, or you have oscillations forever. It can also be that the limit is infinite, but I will currently think of that as being defined but wrong.
But also that doesn't happen here, right? Because you're assuming that the xi's are between -1 and 1. So the average is always between -1 and 1.
Yes, that's true. So in the next game, this will be a possibility, but you're right, not now. So there are upper and lower bounds. So we have to worry about these oscillations mostly, and sort of the wrong limit, in a way it will follow from forbidding these oscillations. Good. So what's the game theoretic law of the large numbers? So this was the measure theory one. The game theoretic one is skeptic has a winning strategy. In this game. Okay, so let's build that strategy. That's the first lecture's content. So let's review a few definitions that we did last week. So we have the sample space, which is going to be all the sequences of moves by reality, in this case, infinite ones. So that's going to be -1, 1, infinitely. Okay. Then there's situations, which we denote by omega diamond, and that is finite sequences of worlds move, and those are going to represent the situations in the game where we have to make a next move. So we have to define the strategy in all these situations. So those will be, let's say star, or if you like, finite length. Okay. Good, so then we can define a strategy. It's going to be a process which is a function, we typically note it by P, from situations to R. And the strategy will tell us in every pass how many of these tickets we're going to buy. Okay, so that defines a capital process, which is how much money we have. And it may seem a little bit redundant, but just let's do it anyway. So the capital process of strategy P in the empty situation, so that's at the start, we're going to say it is 0. That's not quite what we say here, but we're later going to play with the starting capital. So it's nice to have sort of a canonical capital process that we can then translate to whatever we want to start it from. So we're going to, in the book they have a different letter, but my calligraphic K and capital K are sort of too similar. So if it's confusing, I'll try to remind you, then just ask. So the capital process here, but you can, if there's a P on top, it's definitely the one starting from 0. So in the empty situation you have 0, and then in any other situation, so there's already a bunch of xn's, you use this update rule to define it. So you look how much did you have the last round, you look what does the strategy say, and you add the capital that you make this round. Right, so this is an inductive definition of how much money you have in every situation. Good. And if we want to start from some other number, the authors like to call that a stake. But it's just a number. We can think about the process that starts having alpha and then invests according to P. And it will all the time just have the same alpha that you gave at the beginning and whatever P's trading or investing results. Yeah, so the process starting from alpha will be just alpha plus k of p. Okay. This is also a capital process. So now comes the first thing that took me a while to get used to. And that's that they say, let's call capital processes martingales. So, martingale is a process of the form alpha plus k of p or something. Yeah, so that's not how it works in measure theory world. And there are strong connections that I won't go into. But so from this point on, they keep on saying martingale, martingale when they really mean capital process. And they do make a reservation that they only want to use this word in the symmetric protocols. And that's because you have a martingale, then the negative is also a martingale. But that only works out here if you can flip any investment. But here, because we can take m from R, we can always play minus what we had in mind and get the minus of the change in capital. So if we're in the martingale in this sense, the minus of it is also a martingale. Good. So the martingales are a linear space. You can scale them the minus sign. Alright. So let's start with let's do one more definition. So a skeptic can force an event, which is a subset of the sample space, but the sequences of the full game played out. If there is a strategy P such that the capital of P in any situation is positive, and the limit of the capital you have along any path will actually be infinite for paths that are not in this event. So outside this event, you make infinite amount of money. Yeah, so we saw all these things last week, but now we're again in a very specific protocol. Okay, so now we come to the first tool, right? To make a winning strategy for skeptic in this specific event, right? So if you fill this in for the choice of E, then the question here is, can skeptic force this? Can skeptic force the both large numbers? So that's what we want to prove. But the first thing is we're going to make it easier for ourselves to show that if we can show something weaker, we can immediately boost it all the way to this. Okay, so we're going to define a weaker thing, and that is that skeptic can repeat force some event. So the difference between the two is in the second one. So let's call this 1, 2. So 1 is still this one, but 2 We're going to make it easier. So the limit of the capital going to infinity says, well, this, right? And so what we're going to do here is we're going to also allow this, for example. So it does get as large as you want, but there's no lower bound that also keeps on growing. So to say that is, for example, to say the maximum, well, let's just write like this, is infinite on all paths outside of our event. Yeah, so we don't need quite that this limit is defined, because it won't if this thing keeps on oscillating. We just need to have that it does go to infinity. If you look at the right subset of times. So that's called weakly forcing. And the first thing is to show that if we get to weak forcing, we can get to strong forcing. So this is going to be one of the lemmas. Okay. We can weakly force an event, we can force it. So how do we do it? Anyone have a clue? Because this is a sort of cool and might be useful if you want to get a large pension. No hints? So let me give you one way then. So let's fix a weakly forcing strategy B. Right, so that gets us outside of E to any height at some point. Okay. Now choose some C. And let's define PC to be like B, but stop playing, let's say, or stop buying. Let's say trading if you want. So that means from that point on you set n equals 0 after if you would have played P in the game, you make C. So you agree with yourself on this number, and you say, I'm going to play like P. So in any case, in the real protocol, we have to start from 1. So this is what P makes if you start from 1. And we just do like P does until we hit C, and then we stop investing. Which means that may overshoot a little bit, but we are always above C. So this gets us to C. But we need to get to infinity. But we know that whatever C we pick, outside E, P will get us there. Okay? Yeah. So the idea now is to say, okay, let's not pick one C, but let's make C's at large steps. And let's give a little bit of our money to the first C, a little bit to the second one, maybe a little bit less, a little bit to the third one. And then if we are outside E, then the first strategy will get to its C and stop there, and it will have C at that point. The second one will get to the higher C, it will stop there, and it will have its C. It will not quite have its C, it will have the initial capital you allocated there times C. So we're going to build this master strategy that will be summing over a whole bunch of choices of C. And it will be nice to put them at exponential spacing. So we're going to look at 2 to the k. And we're going to invest 2 to the minus k in the strategy that will stop at 2 to the k. And so that would be P of 2 to the k. Good. So the capital